Hello, AraaTech viewers. Today we are thrilled to bring you another captivating segment on reinforcement learning. This topic is a crucial component that we feel deserves attention following our comprehensive reinforcement learning course uploaded a few days ago. We hope you enjoy, share, and subscribe. Thanks once more for your support. Let's start our topic. Deep Reinforcement Learning (DRL) is a subfield of artificial intelligence and machine learning that focuses on training agents to make sequential decisions in an environment to maximize a cumulative reward. Here are some key points about deep reinforcement learning. Reinforcement learning. Reinforcement learning is a type of machine learning paradigm where an agent learns to make decisions by interacting with an environment. The agent takes actions and the environment provides feedback in the form of rewards or punishments, which the agent uses to adjust its strategy over time. Deep neural networks (DNNs). Deep neural networks are a class of machine learning models inspired by the structure and function of the human brain. They consist of interconnected layers of nodes, neurons, that learn hierarchical representations of data. In the context of DRL, deep neural networks are used to approximate complex functions that map observations of the environment to actions, combining reinforcement learning with DNNs. In DRL, traditional reinforcement learning algorithms are enhanced by incorporating deep neural networks. This integration allows the agent to handle high dimensional input data such as images or raw sensor readings, making it suitable for tasks in complex and dynamic environments. Learning sequential decision making. DRL is particularly well suited for problems where decisions need to be made over a sequence of steps. The agent learns a policy, which is strategy for selecting actions in different states, aiming to maximize the cumulative reward over time. Representation learning. Deep neural networks in DRL serve as powerful function approximators, enabling the agent to automatically learn useful representations of the environment's state. This is crucial for handling complex and unstructured input data. Handling complexity. Many real-world problems involve environments with a large number of states and actions. DRL, by leveraging deep learning, can effectively handle the complexity of such environments, allowing the agents to learn intricate patterns and make informed decisions. Training through interaction. DRL agents learn through interaction with the environment. They explore the environment by taking actions, receive feedback in the form of rewards, and use this feedback to update their internal representation, neural network weights, in a way that improves future decision making. Generalization. DRL aims to enable agents to generalize their learning from specific experiences to new, unseen situations. The deep neural network facilitates this generalization by capturing underlying patterns and dependencies in the data. Applications. DRL has found applications in various domains, including robotics, game playing, autonomous vehicles, finance, and healthcare. The ability to learn from interaction makes it suitable for tasks where explicit programming or supervised learning may be impractical. In summary, deep reinforcement learning integrates reinforcement learning principles with the representational power of deep neural networks, allowing machines to learn and make sequential decisions in intricate and dynamic environments. The combination of these two approaches has led to significant advancements in the field of artificial intelligence, especially in areas requiring complex decision making and adaptability. Key components. Agent. The agent is the entity or system that integrates with and learns from the environment. It is the decision maker in the system and takes actions based on its current understanding or policy. In DRL, the agent is often represented by a neural network that learns to map observations of the environment to actions. Environment. The environment represents the external system or context in which the agent operates. It could be a virtual world, a physical space, or any system that the agent is designed to navigate. The environment is characterized by a set of states that the agent can perceive and a set of possible actions that the agent can take. Actions. Actions are the decisions or moves made by the agent in response to its current observation of the environment. In DRL, actions are selected based on the learned policy. The set of possible actions depends on the specific task and can range from discrete choices, that is moving left or right, to continuous actions, that is adjusting motor control signals. Rewards. Rewards provide the numeric feedback to the agent based on the actions it takes in a given state. The goal of the agent is to learn a policy that maximizes the cumulative reward over time. Rewards serve as a signal for the agent to understand the desirability of its actions. Positive rewards encourage actions that lead to favorable outcomes, while negative rewards or punishments discourage undesirable actions. The agent's objective is often to find a policy that maximizes the expected cumulative reward, leading to the exploration of strategies that result in favorable long-term outcomes. These key components work together in a continuous loop. The agent observes the current state of the environment. It selects an action based on its policy or strategy. The environment transitions to a new state based on the action taken. The agent receives a reward or penalty based on the new state. The agent updates its internal policy or strategy to improve future decision making. This iterative process of interaction, learning, and adaptation allows the agent to navigate complex environments and learn effective strategies for achieving its goals over time. The combination of these components forms the foundation of the reinforcement learning framework with deep neural networks, adding the capability to handle high dimensional and complex state spaces. Deep Q learning, DQN, Q function. In reinforcement learning, the Q function, denoted as Q, SA, represents the expected cumulative reward of taking action A in state S and following a certain policy thereafter. It quantifies the quality of an action in a given state. Deep Q learning, DQN. DQN is an algorithm that combines Q learning, a traditional reinforcement learning algorithm, with deep neural networks to handle high-dimensional state spaces. It was introduced to address the challenges of traditional Q learning when applied to complex and real-world environments. Approximating the Q function with neural networks. Instead of maintaining a table of Q values for all possible state action pairs, impractical or for large state spaces, DQN uses a deep neural network to approximate the Q function. The neural network takes the state as input and outputs Q values for all possible actions. Experience replay. QN employs a technique called experience replay, where past experiences, tuple of state, action, reward, next state are stored in a replay buffer. During training, random batches of experiences are sampled from this buffer to break the temporal correlation of consecutive experiences. This enhances the stability of training and helps the algorithm learn more efficiently. Target queue network. DQN uses two neural networks, the online network and the target network. The online network is used to select actions during interaction with the environment, while the target network is periodically updated to the weights of the online network. This helps stabilize the training process by educating the correlation between the target and predicted Q values. Loss function. The loss function used in DQN is typically the temporal difference TD error, which measures the difference between the predicted Q value and a target Q value. The target Q value is calculated using the Bellman equation, incorporating the reward and the maximum Q value, the next state. Epsilon greedy exploration. DQN uses an epsilon greedy strategy for exploration where the agent selects the action with the highest Q value with probability 1 epsilon and explores a random action with probability epsilon. This balances between exploiting the current knowledge and exploring new applications. DQN has been successfully applied to various tasks, including playing video games. That is, the original DQN demonstrated superhuman performance in Atari 2600 games, robotic control, and other complex decision-making problems. Challenges. DQN and similar algorithms may face challenges such as overestimation of Q values and sensitivity to hyperparameters. There have been subsequent advancements and variations such as double DQN and dueling DQN designed to address these challenges. In summary, deep Q learning is a powerful algorithm in deep reinforcement learning that leverages deep neural networks to approximate the Q function, enabling agents to learn effective policies in complex environments. The integration of experience, replay, and target networks contributes to the stability and efficiency of the learning process. Policy gradient methods. Policy gradient methods are a class of reinforcement learning algorithms that focus on optimizing the policy directly. Rather than estimating the Q function, the policy represents the strategy of decision-making process of the agent, specifying the probability distribution over actions given a certain state. Key points. Policy optimization. Unlike Q learning, which estimates the expected cumulative reward for each action in a given state, policy gradient methods work by directly adjusting the parameters of the policy to maximize the expected cumulative reward. Stochastic policies. Policy gradient methods often use stochastic policies where the agent's action selection involves a probability distribution over possible actions. This stochasticity aids exploration and allows the agent to discover a diverse set of actions. Objective. The primary objective of policy gradient methods is to find the policy parameters that lead to actions resulting in the highest expected cumulative reward over time. The optimization process seeks to improve the policy by reinforcing actions associated with higher rewards. No Q function estimation. Unlike Q learning approaches, policy gradient methods do not explicitly estimate the Q function. Instead, they directly adjust the policy parameters based on the observed rewards, encouraging actions that lead to favorable outcomes. Reinforce algorithm. One of the classic examples of a policy gradient method is the reinforce algorithm. It updates the policy parameters by considering the log probabilities of the taken actions and scaling them by the obtained rewards. This process guides the policy toward actions that yield higher rewards. Handling continuous action spaces. Policy gradient methods naturally extend to problems with continuous action spaces, making them well suited for tasks such as robotic control or scenarios where actions are not easily represented by discrete values. Exploration and exploitation. These methods inherently balance exploration, trying out new actions, and exploitation, choosing actions known to yield high rewards. The stochastic nature of the policy allows the agent to explore different actions during learning. Applications. Policy gradient methods find applications in various domains, including robotics, natural language processing, and scenarios where the agent needs to learn complex and adaptive strategies. In summary, policy gradient methods offer an alternative approach to reinforcement learning by directly optimizing the policy of the agent. The approach is particularly useful in situations where the optimal action is not easily represented by a value function, and the emphasis is on learning a robust decision-making strategy. Actor-critic models. Actor-critic models are a class of reinforcement learning algorithms that combine elements of both value-based and policy-based methods. These models consist of two main components: an actor, policy, and a critic, value function. The actor is responsible for deciding which actions to take, while the critic evaluates the goodness of those actions. This combination aims to enhance learning stability and efficiency. Key points: actor, policy. The actor is responsible for selecting actions based on the current policy. It defines the strategy that the agent uses to interact with the environment. Critic, value function. The critic, on the other hand, evaluates the actions taken by the actor by estimating their value. This value function provides feedback on how good or bad the chosen actions are in a given state. Advantages of combination. By combining both policy and value-based approaches, actor-critic models leverage the strengths of each. The policy actor guides action selection, while the value function critic provides a measure of the expected cumulative reward associated with those actions. Learning stability. The presence of a value function helps stabilize learning. The critic's evaluation provides a baseline or reference point, reducing the variance in the updates to the policy. This can lead to more stable and faster convergence during training. Temporal difference (TD error). Actor-critic models often use a temporal difference (TD error) to update both the policy and the value function. The TD error represents the difference between the predicted and actual values, guiding the learning process. Applications. Actor-critic models find applications in various domains, including robotics. Actor-critic methods are commonly used in robotic control tasks. The combination of policy-based and value-based learning allows robots to learn both effective strategies and accurate action evaluation, enhancing their ability to perform complex tasks. Game playing. In the realm of game playing, actor-critic models have been applied to train agents for playing video games. The combination of policy and value learning can lead to more efficient and stable training, enabling agents to learn from both successes and failures. Finance. Actor-critical algorithms are utilized in financial applications where agents need to make decisions in dynamic and uncertain environments. The critic helps evaluate the potential outcomes of financial decisions while the actor adapts its strategy accordingly. Autonomous vehicles. In autonomous vehicles, actor-critic models can be employed to optimize decision-making policies for navigating and control. The combination of policy and value learning contributes to robust and adaptive behavior, diverse driving scenarios. Natural language processing (NLP). Actor-critic models are also applied in NLP tasks where the actor defined the policy for generating language sequences and the critic evaluates the quality of those sequences. This can be beneficial in tasks such as dialogue generation and language translation. In summary, actor-critic models are versatile and find applications in various fields where agents need to make sequential decisions in complex and dynamic environments. The combination of policy and value-based learning enhances learning stability and allows for more efficient exploration of the solution space. Robotics. Deep reinforcement learning has been applied to robotic control tasks, enabling robots to learn complex movements and manipulate objects in the real world. This includes applications in industrial automation, grasping, locomotion, and dexterous manipulation. Game playing. DRL has achieved notable success in playing complex games. Notable examples include AlphaGo, which used deep reinforcement learning to defeat human Go champions. Deep reinforcement learning has also been applied to play video games, achieving superhuman performance in games like Atari 2600 titles and Dota 2. Finance. In finance, DRL has been used for algorithmic trading, portfolio optimization, and risk management. Agents trained with deep reinforcement learning techniques can adapt to dynamic market conditions and learn optimal trading strategies. Healthcare. Deep reinforcement learning has found applications in healthcare for personalized treatment planning, drug discovery, and medical image analysis. It has been used to optimize treatment regimens and discover novel therapies. Autonomous vehicles. Deep reinforcement learning is applied in the development of autonomous vehicles for tasks such as navigation, path planning, and control. Agents learn to make decisions in complex and dynamic traffic environments. Natural language processing (NLP). Deep reinforcement learning techniques have been employed in NLP tasks such as language generation, machine translation, and dialogue systems. Agents can learn to generate coherent and contextually relevant language. Supply chain management. Deep reinforcement learning has been used in optimizing supply chain processes, including inventory management, demand forecasting, and logistics. Agents learn to make decisions that lead to more efficient and cost-effective supply chain operations. Energy management. Deep reinforcement learning has been applied to optimize energy consumption in various contexts, including smart grids, building management systems, and renewable energy integration. Agents learn to adapt energy usage based on real-time conditions. Education. In educational technology, DRL has been explored to create intelligent tutoring systems that adapt to the learning styles and progress of individual students. This helps in providing personalized learning experiences. Computer systems. Deep reinforcement learning has been used to optimize the performance of computer systems, including resource allocation, task scheduling, and network management. Agents learn to dynamically adapt to changing workloads. Virtual reality (VR) and augmented reality (AR). Deep reinforcement learning has been employed in virtual reality and augmented reality applications for creating realistic and adaptive virtual environments. This includes applications in training simulations, entertainment, and immersive experiences. The versatility of deep reinforcement learning lies in its ability to learn from interactions with environments, making it suitable for tasks where traditional programming or supervised learning approaches may be challenging. As research in deep reinforcement learning continues, its applications are likely to expand further across various domains. Sample inefficiency. Deep reinforcement learning algorithms often require a large number of interactions with the environment to learn effective policies. This sample inefficiency can be impractical or costly in real-world applications, especially in domains where each interaction is time-consuming or expensive. Exploration, exploitation, trade-offs. Balancing exploration, trying new actions to discover their effects, and exploitation, choosing known good actions to maximize immediate rewards, is a fundamental challenge in reinforcement learning. Striking the right balance is crucial for agents to both explore their environment and exploit their existing knowledge effectively. Stability issues during training. Deep reinforcement learning training processes can be sensitive to hyperparameters and the learning dynamics may be unstable. This can result in difficulties in converging to optimal policies or lead to oscillation in the learning process. Ensuring stable and reliable training is a persistent challenge. Credit assignment problem. The credit assignment problem refers to the challenge of properly attributing rewards or penalties to specific actions taken by the agent, especially in long and complex sequences of actions. Determining which actions contributed most to the overall outcomes is a non-trivial task. Function approximation challenges. When dealing with high-dimensional state and action spaces, as is common in many real-world applications, function approximation becomes challenging. Deep neural networks may struggle to generalize well across diverse states, leading to suboptimal performance. Non-stationarity. Environments can be dynamic and non-stationary, meaning that the optimal policy may change over time. Adapting to such changes during training can be difficult, and the learned policy may become obsolete or inefficient in evolving environments. Overestimation of Q values. Value-based methods, including DQN, may suffer from overestimation bias, where the estimated Q values are consistently higher than the true values. This can lead to suboptimal policies and impact the agent's decision making. Transfer learning and generalization. Generalizing knowledge from one task to another, transfer learning, or adapting to variations in a task, generalization, remains a challenge. Agents may struggle to transfer learned policies to new but related environments or tasks. Sparse rewards. Learning in environments with sparse or delayed rewards can be challenging. Agents may struggle to associate their actions with distant rewards, making it difficult to learn effective policies. Ethical considerations. DRL systems can inadvertently learn biased or unfair behaviors, and their deployment in real-world scenarios raises ethical concerns. Ensuring fairness, transparency, and accountability in DRL applications is an ongoing challenge. Addressing these challenges requires a combination of algorithmic advancements, improved training methodologies, and a deeper understanding of the underlying dynamics in various application domains. Researchers continue to work on developing solutions to make DRL more robust, efficient, and applicable to a wide range of real-world problems. OpenAI Gym is an open-source toolkit developed by OpenAI that is designed to facilitate the development, testing, and comparison of reinforcement learning algorithms. It provides a collection of environments, both classic control problems and more complex ones, to serve as benchmarks for evaluating the performance of different reinforcement learning approaches. Key features. Environment abstraction. OpenAI Gym abstracts the interaction between an agent and its environment, providing a standardized interface for reinforcement learning tasks. This allows researchers and developers to focus on designing and implementing algorithms without having to redefine the environment details each time. Diverse environments. The toolkit includes a wide range of environments, from simple grid worlds to more complex physics, simulations, and control tasks. This diversity allows researchers to test algorithms across various domains and challenges. Standardized interface. OpenAI Gym defines a common interface for interacting with environments, making it easy to switch between different environments when testing algorithms. This standardized interface includes methods for taking actions, receiving observations, and obtaining rewards. Easy to use API. The toolkit is designed to be user-friendly with a simple and consistent API. This makes it accessible to both beginners and experienced researchers in the field of reinforcement learning, benchmarking and comparison. OpenAI Gym is widely used for benchmarking and comparing the performance of different reinforcement learning algorithms. The standardized environments allow researchers to assess how well their algorithms generalize across a variety of tasks. Community contributions. The toolkit has a vibrant community and users can contribute their own custom environments. This collaborative aspect enables the expansion of the available environments and encourages the sharing of new challenges and benchmarks. Integration with reinforcement learning libraries. OpenAI Gym can be easily integrated with popular reinforcement learning libraries such as TensorFlow and PyTorch, allowing researchers to implement and test their algorithms using their preferred frameworks. Compatibility with Gym extensions. OpenAI Gym supports extensions such as Gym Retro for retro style games and Gym Mojuko for tasks involving physics simulations, expanding the range of tasks that can be tackled. Overall, OpenAI Gym has played a crucial role in advancing the field of reinforcement learning by providing a standardized platform for developing and evaluating algorithms. Its accessibility and versatility have contributed to the widespread adoption of reinforcement learning techniques in academia and industry. Recent advances, algorithmic advances. Researchers are constantly proposing new algorithms and improvements to existing ones. This includes developments in policy gradient methods, value-based methods, and hybrid approaches like actor-critic models. Techniques like proximal policy optimization (PPO), trust region policy optimization (TRPO), and soft actor-critic (SAC) have emerged to address various challenges. Exploration strategies. Enhancing exploration remains a focal point of research. New strategies for guiding agents to explore their environments more effectively, especially in complex and sparse reward settings, are actively explored. This includes methods like intrinsic motivation and curiosity-driven learning. Sample efficiency. Addressing the issue of sample inefficiency is a critical research area. Researchers are working on developing algorithms that can learn from fewer interactions with the environment, making DRL more practical for real-world applications. Transfer learning and generalization. Improving the ability of DRL models to generalize their knowledge across tasks and environments is an ongoing challenge. Techniques for transfer learning, meta-learning, and domain adaptation are being explored to enable agents to leverage past experiences more effectively. Hierarchical and multi-agent reinforcement learning. Research in hierarchical reinforcement learning focuses on enabling agents to learn and operate at multiple levels of abstraction. Multi-agent reinforcement learning (MARL) involves developing algorithms that allow multiple agents to interact and learn from each other, leading to more cooperative or competitive behavior. Safe and robust reinforcement learning. Ensuring the safety and robustness of reinforcement learning systems is gaining attention. Researchers are exploring methods to make deep reinforcement learning agents more reliable and capable of handling uncertainties and disturbances in real-world applications such as robotics and autonomous systems. Neuro-inspired architectures. Some researchers draw inspiration from neuroscience to design novel neural network architectures for deep reinforcement learning, mimicking aspects of the brain's structure and function, such as attention mechanisms, can lead to more efficient and biologically plausible learning. Adversarial training. Adversarial training inspired by the success in generative adversarial networks, GANS, is being explored in the context of reinforcement learning. Adversarial methods can be used for training more robust and adaptable policies. Ethical and fair reinforcement learning. As deep reinforcement learning systems are deployed in real world applications, addressing ethical concerns and ensuring fairness in decision making processes is gaining prominence. Research is focused on developing algorithms that are more transparent, interpretable, and unbiased. Incorporating domain knowledge. Integrating domain knowledge into deep reinforcement learning models is an ongoing research direction. Combining reinforcement learning with insights from specific domains can lead to more efficient learning and better utilization of expert knowledge. The interdisciplinary nature of deep reinforcement learning research involves contributions from computer science, neuroscience, control theory, and other fields. This collaborative effort continues to push the boundaries of what is possible in terms of learning complex behaviors and decision making in diverse and dynamic environments. Bias and fairness. Deep reinforcement learning models can inadvertently learn biases present in the training data. If the training data reflects societal biases, the learned policies may perpetuate or exacerbate these biases. Ensuring fairness in the decision making process is essential to prevent discriminatory outcomes. Transparency and explainability. Deep reinforcement learning models, particularly deep neural networks, are often regarded as black boxes, making it challenging to understand how decisions are made. Ensuring transparency and explainability is deep reinforcement learning systems is important for building trust and allowing stakeholders to understand the rationale behind the agent's actions. Data privacy. Deep reinforcement learning models rely on data to learn effective policies. Concerns arise regarding the privacy of individuals whose data is used for training. Implementing mechanisms to protect sensitive information and respecting privacy rights is vital in the development and deployment of deep reinforcement learning systems. Societal impact. The deployment of deep reinforcement learning systems can have profound societal impacts. This include concerns about job displacement, changes in labor markets, and the potential for concentration of power. Assessing and mitigating the broader social implication of autonomous decision-making systems is an ethical imperative. Safety and robustness. Deep reinforcement learning agents may learn behaviors that are unsafe or lead to unintended consequences. Ensuring the safety and robustness of deep reinforcement learning systems is essential to prevent harmful actions, especially in applications such as robotics, autonomous vehicles, and healthcare. Long-term consequences. Anticipating and understanding the long-term consequences of deep reinforcement learning deployment is challenging. Ethical considerations include the potential for unforeseen societal changes and the need for continuous monitoring and adaptation to evolving circumstances. Accountability and responsibility. Establishing clear lines of accountability and responsibility is crucial in the deployment of DRL systems. Understanding who is responsible for the actions of autonomous agents and establishing mechanisms for accountability are key ethical considerations. Equity and accessibility. Ensuring that the benefits of deep reinforcement learning are distributed equitably and that access to these technologies is not biased or restricted is an ethical concern. Addressing issues of accessibility and promoting inclusivity in the development and deployment of deep reinforcement learning systems is essential. Human in the loop. The role of human oversight and intervention in deep reinforcement learning systems is an important ethical consideration. Determining the appropriate level of human control and ensuring that human values are respected in decision making processes are key aspects of responsible DRL development. Regulatory compliance, adhering to existing regulations and ethical guidelines in the development and deployment of deep reinforcement learning systems is essential. Complying with legal and ethical frameworks helps ensure that deep reinforcement learning technologies are developed and used responsibly. Ethical considerations in deep reinforcement learning are interconnected with broader discussions in the field of artificial intelligence ethics. As the field continues to evolve, ongoing research, collaboration, and the establishment of ethical guidelines are essential to address these considerations responsibly.